Okay, good. So the question is, what if maybe a given text, like Harry Potter book, doesn't contain such natural identifiers, right? So this actually was also a problematic part that we solved in the following way. So we also were trying to analyze if the text itself has some structure, right? So not only about having these SSH keys, but only specific arrangement, for example, of text. Like in this case, it was about some mathematical, simple math questions and answers, and you can replace, for example, certain values with new values. So then actually it's also regarding this aspect, if there are no identifiers in the text, what can we do? So then it's a bit more creative process, and you have to find out what is the structure of this text, and if we could still have such a like a creation of the new structure, and then comparing if the model actually behaves differently on the original structure versus the new generated structure. So, for example, for the Harry Potter book, it might be that we might find, names of the main characters, or for example, maybe like copyright, copyright strings in the pages. So certain values that actually can maybe repeat many times in the book, and then we'll replace them with newly generated versions. But I agree that for natural text, maybe blog posts, sometimes there is no such signal. So then we might have to fall back into the other options. And one of them actually was this generation of the reference set from another model. So this was, I would say, an alternative. It's not ideal because there might be distribution shift, which I think also there are questions about. So also, I think that there were other questions from Sina. So also Sina asks, how can we make green tokens more likely in watermark version of the language models? I mean, how we can, without changing the training data and the structure of the sentences, for example, overusing a word, motivate the language model to use some tokens more. So first clarification is this: the red-green watermarking for LLMs actually is inference. Let's call it test time watermarking. So actually, what you're talking about is how can we make model watermark during training? Actually, here's not the case. So here, during the generations, we force the model, or we call it nudge the model, to generate more the green tokens than the red tokens. So there is nothing, so the watermarking has nothing to do with the training. It's purely inference time operation. In this case of the green red watermarking for LLMs.
When training was training to actually give watermark here.
Sorry?
I mean that during the training process, it was training a way to create watermark.
No, so the training process is staying the same as standard training. So we don't change anything during training. This actual watermark operates purely during generation. Okay, so there's also, okay, follow-up question?
What was lost or something?
Sorry, what's the question?
How do you want to use more tokens when you're inference and not training?
Yes. So here we discussed how LLMs generate the tokens, right? And then we said that LLMs have internally vocabulary, so all possible next tokens that LLM can generate. And then for example, there are different ways how to choose the next token. One of them is just greedy approach, where you just choose the token with the highest probability. Now, what you can do is that you divide this vocabulary into two sublists, so green and red lists. And then what you want from the model, if it's watermarking, to generate the tokens from the green list. So then you wouldn't generate this, in this case, fine as the next token or the next word, but you would choose one of the words from the green list. In this case, it would be great. So you wouldn't choose the highest probable token, but in this case, second one, which actually belongs to the green list. So it's changing which tokens we actually choose for the next returned token. Exactly. So actually how it works is that you basically have logits. So actually this is similar to what we discussed in Bitmark. So here is in a simple scenario of the bit generation, so bit by bit generation. So we operate here on the level of logits. So this is standard prediction. So model predicts what are the probabilities P1 and P2 for the bit, for bit 1 is P1, for the bit 0 is P0. And actually then we nudge this model to generate bits 1 by adding this delta parameter to the logits actually. So this nudging actually is performed in the logit space, let's call it. So all the tokens from the green list would be with the probability which was changed by addition of the delta to the logits. So delta nudges these models to generate more of these green tokens. We also have hard case that you say that only generate tokens from the green list. However, this degrades the performance of the model because then you kind of force the model to only generate tokens from the green list. Give you an example, you might have, for example, that, okay, the US president was Barack Obama, but then if, let's say, Obama falls into the red list, you wouldn't generate Obama, you would generate Barack something else, which kind of doesn't make sense, right? Probably in this scenario. So then you don't force the model to generate only the tokens from the green list, but you nudge the model with this delta. So actually this softer version ensures that we don't destroy the quality of the generations. And also, Sina asked many questions. Number 3 is regarding serum. So could you again explain what is the intuition behind each of the terms for the loss function? So let me go to serum. So actually in serum we have this actually 2 loss terms, and the final is just combination of both, right? So what we want with the serum loss are 2 things. So first is this loss sub W. This is for the watermark images. So the idea is that we want a model to still identify watermark image even if we perturb the image. So here, so x star, so the first term minus log of f of x star is a clean image. So this is purely just to make sure that this actually detection works. Second part actually is that we transform the image. So here we use this replay buffer, prioritized replay buffer, to add the transformations of the image that actually cause the biggest problem for the detector to classify a given image as being watermarked. And this is quite costly because during the training, you have to generate these perturb samples. So then we limit that to some specific number of m samples. Also, actually, we have this log of x sub t star. Actually, this part is that we already, before the training, prepare many of these watermark images that actually are also transformed. For example, with the compression or addition of the noise. So actually, then you have to generate these things on the spot. And this term is basically the whole loss is to just ensure that our detector of the watermark can find out that, okay, it's actually our watermark images. Now we do exactly the same symmetrically for clean images. So also we want to find out that if image is clean, we classify this as being clean, even if we augment this clean image. So for example, we add noise to the clean image, we compress the clean image, it still is a clean image, non-watermarked. And then we equally weight these 2 losses, so loss L sub W and with loss L sub M.
Yes, so the third term and the first one, they are only one item, but the second one has many different.
Oh no, so actually, so basically, we compute. So we choose one of the pre-computed samples for the given iteration, but there are many of them. And also we choose some number of this some number of this okay, we have to choose some number of this transform that actually are on the spot are transformed. Mhm. Okay, and then could you could you please explain the components in the architecture on slide 65? So slide 65. Okay, so here, so what's happening from the beginning? We have a model which is generating the tokens, so autoregressively, and then we have these tokens here arranged in this way. So tokens are generated one by one as an index in the code book, and then we dequantize these tokens, meaning that we change from the image representation, so just image index of the token, to the codebook representation. So actually, codebook is in this case for var 4096 different values per vector of the values. So we have then the feature map. So each token index corresponds to this whole vector in the feature map. Then we decode this feature map to the image. So we go from the latent space feature map through the decoding, which is basically based on convolution operations. We go to the image space, like pixel space. So we have the image. Now we also do this decoder inversion. So now we go from the pixel space back to the feature space. And then this returned feature map should be as close as possible to the feature map before the decoder did, this blue decoder. And then here we train also this inverse decoder so that it really should perfectly, or as close as possible, recreate the feature map that was actually given to the decoder. So here you could, in principle, use encoder for that. However, we found that it's much better if you train the encoder. You just further fine-tune that to give you much better feature map than with just encoder.
Actually, we can see there some of them are similar together. For example, we have two tree, we have one.
Sorry?
The numbers in tokens of T of C.
Yes, these are random numbers. This is just example. Yes.
So they should be distinct ones.
So they also can they can also repeat. So basically, you have here token 5 twice, token 1 twice. So, but it's just example that these tokens can repeat, right? Because you have like 4096 tokens for var, for example. Then, of course, like image might have some repetitions of some tokens, so yeah. Okay. So actually, then actually have data provenance. So here we just take the image, we revert the image to the feature space, feature map, and then we quantize the image. So so basically, how do we quantization? So we find what is the closest token representation to the given feature map. So we just quantize this feature map, and then we have this code book with all possible tokens. So we ultimately find the tokens and then again dequantize to the feature map. And then we compare how close is feature map to the requantized feature map. And this actually is our quant loss. Okay. Okay. So what's your question? Okay. So it was okay. Your name was Umer, right? Okay. So was it really okay? Is it the last question on the first page? Is it the last question on the first page? Okay. 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 So basically the question is So if the next models are trained on the watermark data, especially radioactive marks, then does it degrade more or less the model performance? So actually here, the radioactive marks are ready to trace how data is used in the generative AI ecosystem. So here we don't have any built-in protection. So watermarks also are supposed to be not invasive, meaning that we don't want to further destroy model's performance. It's more about tracing if the given data actually was used in the next models for training. So here, how we can imagine that is, let's say I'm OpenAI, and I generate many of these given, let's say, images, right? Then somebody, posts these images online, publishes them, and trains a new model on this watermark data, right? But then the model 2 generates more data and also puts them on the internet. And somebody takes this new data too, trains model 3 on this data, right? And then model 3 generates some more data, right? And then OpenAI would like to know, hey, does this data in some way, is it derived from my model? If so, then they don't want to train on this data because this degrades model performance. So the bottom line is that we use these radioactive marks to trace the whole chain of derivation, how you can derive more data from a given source data, and doesn't inherently protect you from training on this data, should not degrade even more the performance of the new models, but for the original party who creates this data, then can ensure that they never would train, okay, hopefully, wouldn't train on the data derived from their own data. This is one more aspect, is that these radioactive marks have some decay, right? So if you have, for example, maybe fixed number of like 5 generations and training of the models. So let's say model 1, 2, 3, model 5. Model 5 generates some data. Might be the case that watermark decays, and this radioactivity actually is not observable in the outputs from model 5. So watermark might propagate to outputs from model 2, model 3, but does not propagate to, let's say, model 5 or maybe model 10, which kind of also is natural, because if you process this data so many times, then probably doesn't really have that much of the source data or this source radioactivity. So maybe then it's safer for training. Yes. So the question is, what makes watermark radioactive? So what we found as of now is that one of the properties is that you repeat the same pattern, in this case of bits, within a given image and across many images. And actually this is something that we find to make watermarks highly radioactive. So we talk about this aspect here, that if you have standard watermarks, usually they add specific, for example, noise per sample. So there are watermarks, for example, like let's say serum, okay? But for every single generation or every single type of generation, they have different noise added. And then kind of there is no preserved pattern across many samples, even across a given sample. And then if you have these different patterns for all the generated samples, then model has nothing to learn, right? Model has no incentive to learn because this pattern occurs once. So then why should I learn that, right? And in this case, what makes actually watermarks radioactive and also learnable is that you have this specific pattern, it's repeated many times, so model is supposed to learn the general patterns and actually learns these patterns. Mm-hmm. Okay. 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 So yeah, we can start maybe over there. Yes. Ahmed, yes. Okay. Was it the okay? I see. So the question about privacy attack on VAR, this one. So Ahmad was asking regarding attacks on vars. So it's short answer. As of now, the attacks works only in the white box access. So if we have access to the model parameters, and we can also generate this images token by token, so we can give to the model prefix. Only in this setup this attack works as of now, and we haven't explored how to extract the memorized images in the black box fashion.
Yes, the lecture were all enough white box as well. Some white box methods that we
So
there wasn't any standards on that one.
on black box, you mean?
Yeah, let's say the example that we mentioned before on the OpenAI that we use green and red, there was also kind of white box then black box.
Okay. So so here indeed, like we focus in many cases on having model access. However, for example, you can verify if watermark exists in a black box fashion. Now, also, we now work on methods that would detect the data sets used for training in the black box fashion. So, for example, for the methods like the data set, we currently assume we have access to the token probabilities. However, latest APIs do not provide the token probabilities. So then one way how we think about is how to solve the problem actually is by estimating or approximating token probabilities in a black box fashion. So there are many ways how to do it. One of them is that you might have some reference model, and then you would check, okay, for the next token, what is the probability of this token in other model? So this might give you some estimation of how the given model gives this probability to the original token. So there are ways how to transfer some of these methods from the white box fashion that we discussed in the lecture to the black box scenario. Okay. So the question also from Ahmad regarding the memorization. So I think the question is that if we give to the model memorized sample, does the model detect this as being generated by this given model? So for example, we have this memorized butterfly, monarch butterfly, and the question was if we give to the model the sample which is original and sample which is extracted, would the model in both cases say that the sample is generated? This is the question. So actually, it occurs that if we operate on the level of these tokens, and if we go to the method which actually checks the codebook, so how we generate these images, do they come from the codebook or not? So if we go back, so we start with the image being natural, it occurs that on the level of codebook, still, it is farther away from the codebook than generated image. So these images, okay, visually to us are almost the same. But then if we decompose them, if we then go back to the representation on the level of tokens, naturally they have a slightly different representation with generated images being closer in the token space to the codebook than the natural images.
The normalization approaches that we had, if we use some kind of thresholding to detect whether it was generated or it was the real image, this one would fall very closer than the image that was not memorized. So all the threshold would be based on the images that weren't memorized. And this one you would detect as generated one, but it was a real image or
yeah, so actually, so we check that, and then as of now, we find that at least in the case of vars or yars in general, we find that you can distinguish between natural images and generated images, even if they are memorized. But probably, if the model would memorize them even more, so like if all tokens would be the same, of course, in this scenario, we would have basically false positive in the sense that we would identify natural images for training as the generated image, right? So at some point, this boundary might blur because of the perfect memorization on the token level of this given image. As of now, it's not perfect, so we still can distinguish between the natural versus generated image. Okay, so this was for Ahmed. Okay. Okay, maybe over there. Sorry? Anika. Okay, good. Anika. Hmm. Okay. Mhm. Okay. So actually, Anika asks about unlearning, and then the question is, if after unlearning, our methods for provenance would still detect this unlearned sample. Is the question? Okay. So our method on provenance tracing can be thought of as an auditing tool. So then once, as you said, somebody requests that the data is actually to be unlearned, then we might verify if this actually unlearning was successful by trying to identify the training samples in the model training set. So in principle, if it's a perfect unlearning, then you should not have this signal from the initial sample. So yes, I think this could be indeed like this could be a way to evaluate how good the unlearning was. Mhm. Yes. Mhm. Okay, so also actually in this lecture, I mentioned one important thing is that when do we apply unlearning? So as of now, where it would be really useful is especially to unlearn the memorized samples verbatim, right? So for example, if the model memorizes this face of the woman, then we should do unlearning on this specific sample. There is a problem with that, namely removing some memorized samples actually also degrades the model's quality. So here there is a trade-off. So for the model providers, as of now, they optimize for performance, and they don't really optimize for data copyright rights. And naturally, of course, it's still like, I would say, relatively fresh technology. So they want to optimize for model performance. So I would say that unlearning on the level of verbatim memorized samples, I think is valid. And in some cases, we will still observe that it degrades model's performance, right? Now, if we would unlearn a large portion of this data, then usually the model's performance suffers quite a lot. So I would say we observe that unlearning is, or in general, like limiting how much model learns from the given data set or data sets, degrades performance quite substantially. So ultimately, I would say that these provenance methods, since they operate on the also like samples that can be increased, you can have more and more evidence, then these actually methods should really detect this data set used for training very effectively. And then unlearning, I would just use for the specific cases that you unlearn, like the sample is memorized purely. But then, even if sample is unlearned from the verbatim memorization, then it still is to some extent in the model's training set and should be detected. But if you would like to have full unlearning that the sample is totally not detectable, of course, then you should test it with our method based on provenance, like data inference, if the data was or not in this training set. Okay. So this was for Anika. Okay, good. Maybe now this side. Okay. Is Mahad Ahmed?
Yeah.
Okay. Um, So I think that I explained this question while answering question regarding red-green watermarking. So, okay, just to summarize, so we do this soft nudging. So we ensure that we select more tokens from the green list and the red list, but we don't do it in a forceful manner, meaning that we still enable the model to select red tokens because we only use this delta value to increase the probability of outputting tokens from the green list. So it does not destroy the model's performance. So it's not about failing, it's about how much you enforce on model that you have the green samples versus red samples. So for example, okay. So here also I gave an example of the text with watermark, right? But not all the samples are in green, meaning that, you know, in some cases it kind of makes sense to still generate red tokens because otherwise the text might be of much lower quality. And there was this example of the Barack Obama, right? So if we'd always force the model to generate only the tokens from the red list, sorry, from the green list, then we might say something not like Barack Obama, but something else, but doesn't make sense, right? So we still would like to give model possibility of generating tokens from the red list to preserve the high quality of the answers.
Regarding the delta and the benchmark model that we have, they use different scalings. So in different scalings, it might be difficult for the model to be certain or uncertain. It might be different from different scales. So we dynamically change the delta per scale.
So for here, actually, we keep the delta the same. We don't change delta per scale. But actually, parameter delta controls the quality of the outputs. So like to answer your question, Mahmoud, so if you set a higher delta, then you improve the quality of the watermark. So watermark is stronger. However, the text is of the lower quality. If delta is smaller, then watermark is weaker, but you have also higher quality of, in this case, either images or text. Okay. Okay. So we can move on to next question. Go ahead. Okay. 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 So the question is how much of radioactive watermark we add to the training data so that it's still model is still generating watermark data. So we tested actually for bitmark how much we need to really use of the watermarked images in the training of the model to really make the model being radioactive. So what is the point here is that bitmark is highly radioactive, and even for something like 5%, or even I think we went to even like 3%, I don't remember exactly, but a very small percentage of the whole training set makes model radioactive. So here, I would say that it's one of the parameters how much a given model is, how much a given watermark is radioactive. For bitmark, as of now, we observe is the among other watermarks is the most radioactive watermark and requires the fewest number of samples in the training set to make the model radioactive. But it's really in the range of like, let's say, a few percent. Like, I think 5% is for sure radioactive. So for okay, I would say that for bitmark, parameter that makes also the bitmark more radioactive is also delta, because then actually you have more of these bitmark patterns in the generations. So if delta is higher, then you force model to generate more of these green list bit sequences. They occur more often in the generated images, and also then, so think about it this way. You have a number of samples that are watermarked, the radioactive. So if this given a bit sequence which actually determines radioactivity is repeated more often in a given image, like more frequent in a given image, also then the watermark is stronger, has stronger radioactivity. So delta, the higher delta also actually makes watermark not only stronger, but also more radioactive. Okay. Any more questions? Okay. Wait. I think that probably should finish very soon, right? So maybe yes. I think it's Nima's and Maitri's session. Okay. Go ahead. Okay. Adip. Okay. Atip. Okay. Mhm. Okay. So actually, so indeed, you can find out what is the sequence for the bitmark, for example, that is some sequence of bits, right? And now it's still difficult to remove these bit sequences from the watermark. So actually, we did run, of course, experiments, and I would say it's relatively robust watermark. So now the question is, why would you remove the watermark, right? So yeah, yeah. So what I'm saying is that um, you still repeat the same pattern many times, right? Removing the same pattern from a bitmark still costs you a lot of effort because the bitmark sequence of bits is embedded in the given image like multiple times. So then actually this also makes the watermark highly robust and robust to augmentations like image cropping, image blurring, and so on and so forth, even some watermark removal attacks. Now, why? Okay, the question is, why would you why would you like to remove this watermark, right? So maybe you are an adversary that basically still would like, let's say, OpenAI to train on their own images, right, or their own content. So then, how many of these images can you really like remove the watermark from? So if we talk about the scale of the internet data, it's humongous. Just removing the watermark, which is still costly, from a few images does not really impact that much training of the huge models, right? So I think that here, also what we argue with Bitmark is that the watermark embedding and which kind of bits you choose and how many bits you choose for the watermark can be chosen by the given company and not even revealed. So then it's also like maybe a bit more difficult to find out which exactly these bits are embedded for the given watermark. And then this also becomes a bit more difficult to find out how to really remove the watermark. And the second thing is the question why, right? So if I'm OpenAI, if somebody removes like a few of these watermark images, like remove the watermark from them, it doesn't really impact my training that much. Does it answer your question?
Yeah.
Okay. I think that the point is really to ask the question, what is the purpose, right? Like what we would get out of this removal. To what extent would it harm, in this case, what OpenAI, for example? And in this scenario, not much. If we talk about like internet scale data. Okay.
Let's say,
49. Okay.
yeah, each element an image, is this noise fixed for each element, or is it for each generation?
So actually, it's different noise for every single image, every single generation. It's random noise.
The way that to find which element which noise, which image, and they use like for this, they use this noise like a signature of that element.
Signature of the diffusion model, you mean? So basically, what's happening with Serum is that this noise addition that we do is adding static noise. So watermark noise is static. So actually, this makes this generation process in diffusion models to add the watermark to the output from the diffusion models. So here, I would say the main point is that we have static watermark noise for Serum. But when we train diffusion models, then we really add always random noise. So even actually here in the generation from Serum, what we actually do is that we add watermark noise, static noise, to the random noise. So actually this initial noise is totally random.
If you're adding it together, maybe isn't it the case that maybe in a case, for example, the initial noise or the random noise can cancel out the watermark noise because it is being optimized and it can be a way that maybe cancels watermark noise out?
So since this is random process and we have the latent space something like 32 by 32 by 16 channels. So actually you have really like 16,000 roughly of the possible values. So probability of this canceling out is almost zero. I mean, it's zero. Okay, any more questions? Okay, go ahead.
I have two questions.
Sorry?
Taking language model watermarking,
Right.
marking the vocabulary with green and red restrict the expressive power of the model.
Right.
The inferencing.
Right, it does. So so what we talk about this here parameter delta, but it's the same for watermarking of LLMs. So you have to adjust the delta so that you don't harm too much this, as you call it, power of expressiveness or like quality of generations for LLMs.
So in vision models, we are doing watermarking, right? So if you use compression algorithms like JPEG or
Yes.
something to transfer the data,
Yes.
does the compression reduces the presence of this water?
So slightly yes, but what we see is that this is for Serum. The watermark still is highly detectable. It's TPR at 1% FPR. So, we do train this detector of the watermark for Serum to be robust against such augmentations. So we do it in the way that we want this to be robust, and then it actually is robust by design to such augmentations. What's your name?
EMA.
Okay. Okay. Maybe from there. Okay. 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 Okay, so why do we use square root of alpha and square root of minus 1 minus alpha instead of just alpha and 1 minus alpha? So this is done in the same way as in diffusion models. So also we talk about the addition of noise. So let me show you. So actually here we talk about how we add noise in diffusion models, right? So we just follow the same procedure in Serum. So also we do this with the square root of 1 minus alpha and alpha. What is the explanation is that the x and the epsilon are a standard deviation, and actually this alpha sub t is actually supposed to control the variance. So basically this is this proportions of the variance, and then basically we just square root them because ultimately here we influence the standard deviation. Yes, exactly. That's basically gets squared. And then could controlled memorization be implemented during training? For example, penalize high-risk samples, or is it only an auditing method? Can something similar be done for watermarking? So we talk about controlled memorization in the lecture as maybe future directions. This was this actually part. So we said that maybe we have this controlled, some way of controlling what is memorized. And here, actually this memorization detection and also control here in this case would happen during training. So during training, we would like to limit how much a given sample influences the model's training. So ultimately, what we kind of envision is that we would like to control how much, for example, a given model learns about Harry Potter book. So we don't want model to maybe learn the whole book by heart, so meaning word by word, but we would like model to, for example, have some useful representation of the book, some maybe small knowledge representation, maybe some small, let's say, vector space that can answer questions about the book, for example, like who are the main characters, who are the friends of Harry, and so on and so forth, but does not have to do that by learning by heart the whole book. So this actually controlled memorization, I think that intuition is that it should be done during training. And now how can we implement that? So we just learned about privacy, and one of them being the threshold privacy with clipping the gradient, adding noise. Now what we observe is that for these models, if we clip the gradients and add noise, this kind of destroys the model's performance, like decreases the performance by like 20, at least 10%. So of course, if you are a model provider, you don't want to be 10% or 20% worse than the competition. So this is not a viable tool or tool that people would use in practice. Now, what we here think about is maybe instead of using the whole DP framework, maybe, for example, you can just do clipping of the gradients. So if the gradients have a certain magnitude above a certain threshold, then we would clip the gradients to ensure that the model does not really train on these samples to the point of memorizing them verbatim.
The magnitude of the gradients is the problem, but this data is repeated lots in the trains. So it's not memorizing one image on one.
So there are different reasons why models memorize samples. One of them is being indeed sample is repeated many times, and indeed, like it was shown for different models, that if you repeat a given sample twice, it's memorized much more if the sample is only once in the model. But other aspects can be, for example, image is a bit of OOD, meaning auto distribution, so different than other images. And model might think, okay, I have never seen such image, maybe it's important, I just memorize that, you know. So there are also cases where, you know, you have, for example, samples that are mislabeled or miscaptioned, and then the sample is also more memorized. The example of this woman, Anne Graham Lotz, that is like face of this woman is actually memorized. We don't know why it was memorized. Even though caption is correct, sample was not repeated many times apparently in the model's training set. Somehow still model memorizes that. We don't know why. And I think, sorry? It's not. So we don't know. So we have to, still there is, I think, research, very active research on this, in this area to really understand why and how these generative models memorize training samples. Okay. More questions? Okay.
I know that the data has watermarks. Is there anything you can do about this? Or do I just have to throw the data?
You mean if data has watermarks? In what sense?
Trainings.
Ah. You can, right? So like nobody forbids you, right? But here, if I'm OpenAI, I don't want to train on this watermark data, which might come from my own models, because it carries the biases or some, harmful content from previous models generations. So then actually it's for me like very fast way how to filter out samples that I would use for training. So the the goal actually is that this is my data that I generated, and I would like to find out if somebody trains on this data as well. So actually the goal here is that if you train on my data, then I would find out.
So there's nothing to like denoise the data and the watermark before training.
There are methods. However, I think that if you just operate on the scale of the like internet size data, removing watermark from large number of data points is just prohibitively expensive. Also, this related to other question that watermark can be only in a few samples, and still the model becomes radioactive. So even if you don't remove this watermark from a few samples, it still kind of poisons the model. Okay, go.
On second question, bit from the first, like you said, few questions.
Sorry, so what's your name?
Pratyush.
Pratyush. Okay, Pratyush. Uh, let me see. On the second page? Okay, fifth. Okay, okay, see. There is PRRR. Okay. Okay. So yeah.
You said zero watermark are static ones, right?
Yes. Yes. So actually we call it watermark forging. So somebody might just pretend that actually this image, or in this case actually image, would come from the other user, right? And I think that this is indeed possible. So we showed actually that it's possible to forge some watermarks. Now, what is I think very interesting is this, that you might actually detect if a given image was forged or originally created. So you have a kind of different number of possibilities. Image is clean, no watermark. The image is watermarked. The image actually was watermarked, but watermark was removed. The image was clean, but somebody added the watermark, forged the watermark. So thing is that if you remove even the watermark, or if you forge the watermark, like you said in your case, that you pretend that actually this image comes from a given user, then we find that there are still traces that can help us to analyze if actually the image is truly watermarked from the generation, from the get-go, or was it just forged? So then we currently work on these aspects of how to really differentiate which instance of the image we are dealing with. So ultimately there are still traces that we can detect to finally find out which instance of the sample we are dealing with.
On these questions, like coding, can we use coding for that watermark remove? If the sample size is not that big.
Pruning of the what?
Basically, a data set augmentation to remove that watermark issue.
So what we actually show always for watermarks is that no, if you do any of these augmentations, so clean, rotate, JPEG, anything, then the watermark is still retained. So we at least ensure that for the simple augmentations, like simple operations, perturbations, the watermark is preserved. This is kind of standard. If you create a new watermark, you have to show this. Okay, go ahead. Sorry. Rania, okay. Okay. Arania. Anania. Sorry, Anania. Sorry. Okay, I got it. Okay. Okay. So Ananya asks, how do we differentiate harmful memorization from useful learning? For example, if a model must remember general patterns from the data, but when does that become privacy leakage or copyright risk? Copyright risk. So I think it's an excellent question. Um, um, so, okay, how I think about this is models also have parameters, right? And then these parameters are kind of for model storage, right? And you have to decide if you store in these parameters individual samples, which is this kind of harmful memorization because it's unintended, it memorizes individual samples, versus you basically memorize general patterns. Now think about that this way. The number of images in the internet is humongous. So even if I have model with, 1 billion parameters, I cannot really store in this model all images from the whole internet, right? So models should not learn, should not memorize individual samples, but should learn general patterns. And then we should ensure that the model parameters are used to store general patterns and not individual samples. Like, why should we remember the whole Harry Potter book? The book is there on the internet, right? So there is no point in memorizing the whole book. We just learn knowledge about the book. So we store some concise representation of the book in the parameters of the model, and this should be really, really the main point. Now, how can we differentiate between the harmful versus useful? So if I'm able to extract from the model large portion of the given sample, like of the given book, then it's harmful, right? We don't want that because also actually okay, in this case, what is the point is this. I want to read Harry Potter book. I don't go to a bookstore to buy a book. I just go to Hugging Face, download Llama 3.1, and then generate the whole book. And it's actually cheaper than going to the bookstore. So this is copyright violation, at least according to my law. Lawyers might discuss this ad infinitum, but this is kind of copyright risk. So, but if I'm even able to generate a large portion of the book, it's probably still a violation of the copyright. However, for example, there is something like Google Books. You can search for different books on Google Books. Google Books actually gives you kind of like a few pages of the whole book, and they were judged in the US as being so-called how is it called fair use, meaning that it's transformative. It changed books to something that is searchable, and this is not like copying the book, but exposing some value about the book, some knowledge about the book. So you can even search for the whole book, what kind of phrases are in the book, but you don't generate the whole book. You don't give, as a Google, the whole book to the any user. So I would call it that this is fair use, but if you generate the whole book, it's a copyright risks at least. Um, um, so also there is question about augmentation. So as we saw many times, the watermarks are robust to these augmentations. Okay. Yeah. On the second page or first page? Probably two more questions and we are done, I think. Right? Okay. Sorry. Is first page? Second page. Can you speak up your name? Sorry. Ready. You say first page. Okay. Um, Okay. Mhm. So actually here, hmm, hmm, okay, so actually here we have to ensure that our generator, so the question actually is, what if we generate the held out set using the same model? So actually, of course, this is our approach. So we never generate this new text using the target model that we analyze. So then actually we have to also ensure that we know exactly what data was used to train a given LLM for generation. So we don't have this problem of inflating the score because of using the same model. I think one more question. Okay. Okay, what's your name? Edwin? Yeah. Let me just yeah. Okay. Redwan Ataullah? Okay. Yeah. 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 So actually, yeah, so this is the problem to discuss. So usually it's no, like maybe author like J.K. Rowling for Harry Potter book, maybe she had some drafts of the book, but in other cases it's not possible to get this drafts of the book or like some held out set. So this is why we invented these new methods to generate the held out set, like through the central identifiers or through generation of these new data sets, as was mentioned for the last question. So, okay. Um, I think last question. Okay. Go ahead. Second page, first question. Okay. Um, mhm, mhm. So actually, the watermark is not sensitive to scheduler or sampler because it operates. So basically, the injection is at the very beginning, right? Before we do even any uh, diffusion process. So then actually the watermark survives. Okay, the watermark is still there using that doesn't really it's not really affected by which sampler we use or scheduler for this generation. Mhm, mhm. So actually also the question was what's happening if we, for example, have these natural traces, like in the quant loss. So actually here we also check that even if you do some augmentations like JPEG or some noise addition, then still this quant loss actually gives you a signal that a given, in this case, image was coming from a given model. So this actually method is also the quant loss method actually is also robust to common perturbations. Okay, maybe last question. One more question. Okay. What's your name? Shira. Okay. Okay, so this is okay. Okay. Yeah, so it was the same question as the previous one, and this is the answer. So even despite augmentations, we are still able to detect these images coming from a given model. Okay, I think we should finish for today. Thanks for staying, and hope to see you next week for the assignment discussion, and also we have follow-up, I think, to this as a tutorial. Okay, see you next week. Thank you.